Hello, and welcome to this Richardson RFPD and ERZIA webinar. My name is Katie, and I will be your Global Spec moderator. Now let me introduce today's presenters. With us today is David Diaz. David is a Managing Director at ERZIA Technologies. Also joining us today is Noelia Santos. Noelia is the RF and Microwave Engineer at ERZIA Technologies. To read more about any of our presenters today, please look at the speaker bio window right next to the main presentation window. And with that, I'd like to pass things along to David to get us started. So David, go right ahead.
Thank you, Katie. Thank you, everybody, for joining us today in this webinar. So today we are going to talk about accurate noise figure measurements in Ka-band low noise amplifiers, specifically focused in Satcom applications. So I will start with the introduction, giving a little of background of the motivation of this work, and then Noelia will explain you the different technical parts of the presentation, like the comparison of Y factor versus cold source measurements, calibration and instrumentation setup for the measurement, an example of measurement set for Ka-band amplifiers, and then I will take back the word for the conclusions, and we all together will go through the questions and answers section. Okay, first of all, a few words about us. We at ERZIA are RF and Microwave private company. We are located in north of Spain, in Santander, and also we have a subsidiary in Alexandria, in Virginia. So we are very focused on the design and production of RF and microwave devices, especially active devices like amplifiers, but also filters or other more complex units like converters and integrated microwave assemblies from low frequency up to more than 1 gigahertz. And we are very focused in high reliability and high performance of our units. So our main markets are electronic warfare, radar, and Satcom, also with a strong presence in test and measurements, telecommunications, and space. So we have a catalog of low noise amplifiers, more than 80 devices, COTS, much others custom made for customers around the world. So we have a strong motivation to accurately measure our designs and our devices in both design and production stages. Traditionally, we have used different methods, including Y factor and some other methods provided by the test instruments manufacturers. At one moment in time, when we are designing LNAs and we are growing in frequency and decreasing and minimizing the noise figure, we found that measuring with precision is not a trivial task, especially when the noise figure it's being close to the uncertainty of the measurement itself. So for noise figures above 3-4 dB, this is not really critical, but when you start going below 2, even below 1 dB, then the accuracy of the measurement, and especially at high frequencies, starts being very important. We had a practical example a few years ago when we were finding ourselves with a very good LNAs for Ka-band with typical noise figures in the orders of 1.2 to 1.4 over the whole Ka-band. With this hardware, we were competing, we were bidding in several projects, and we knew that those amplifiers were in the state of the art. We know that there are other technologies in RID right now, but not yet in production. So we knew that the performance of the amplifiers was going to be very good, and the competition might have equivalent amplifiers, but not really better, or might be equivalent. So we found ourselves in these competitions having to justify and having to prove our numbers, because a tenth of dB was the difference between getting the contract or not. And we had to demonstrate with accuracy the value and the exact performance of our devices. So we decided to implement the most accurate and traceable measurement technology available in order to improve the performance of our Ka-band LNAs. We have used our own laboratory instrumentation, but we have also counted with the kind collaboration of Keysight. They lend us some of the newest and most performance instrumentation at the moment. Thank you, Ignacio Ruiz and Héctor Carreño and their teams. And using those instruments, we arrived to the bottom line of the noise figure measurements, and we really wanted to take the most of our devices. So now Noelia will explain you during the next minutes our findings, our experiences in this area, and how this help us to measure noise figure with great precision. So Noelia, whenever you want.
Thank you, David, and hello everyone. So now we will present the Y factor versus the cold source measurements. So we will compare the two techniques. The first one is the Y factor technique. It is one of the most popular methodologies. We have to test the noise figure. There are two main reasons. It is quite simple and the calibration is very fast. It is suitable in systems with high values for the noise figure or where accuracy is not very required. The drawbacks are the input matching of the DUT, which is usually not very good for LNAs, and the low accuracy at millimeter waves. The second one is the cold source method. It provides the best possible accuracy if you use a power meter for the calibration instead of a noise source, and a source correction technique is applied. The impact of the DUT input matching error is minimized, and it avoids a limitation in the measurement of bandwidth. The bandwidth is narrower for the noise source, so it is better to use the power meter. The drawbacks are that the calibration is slower and the equipment is quite higher than using the Y factor equipment. Here we have a table comparing the Y factor using the noise source and the cold source method. In the second column we have this method with the noise source, and in the third column we have it with the power meter. So the advantages of using the Y factor, it is in the first column. There is a large diversity of equipment using this method, and the calibration is very fast. The disadvantages are related to the use of the noise source. So you have to choose a very good noise source with a good ENR, depending on your bandwidth and your noise figure. Then you have the effect of the DUT mismatch between the noise source and your DUT when you are applying the on and the off states. Also, there is a problem with the reference temperature, which must be 290 Kelvin. If it is not the case, you have to apply a correction. The linearity of the DUT in detectors are required to avoid uncertainty. And finally, we have a low accuracy above 45 GHz due to the jitter. In the second column, we have the cold source using the noise source. So the advantages are that the accuracy is very good and the calibration is fast. The maximum noise bandwidth we can use, it is 24 MHz. The disadvantages are in common with first column because we are using the noise source. So we have the problem of the choice of the noise source, then the effect of the noise source and the DUT mismatching, also the low accuracy due to the jitter, and we have two new disadvantages related to the equipment. Those are that most equipment does not have this option, and the second one is the price. Finally, in the third column, we have the cold source using the power meter. So this one provides the best possible accuracy. There are no errors related to mismatching and noise parameter effects. Also, the power meters are broadband, so they are easier to find in the market. The disadvantages are that the calibration is slower. So, for example, the maximum noise bandwidth we can use it is 4 MHz. And then the other two disadvantages are in common with the second column. It is the option availability in the equipment and the cost. So the selection of the measurement instrument is also a key factor. We have chosen Keysight PNA-X family of network analyzers because of several reasons. Some of them are that the source corrective technique provides the best noise figure accuracy. Then the power calibrations are fully matched, corrected. The PNA-X receiver is the most accurate one in the market thanks to its linearity. And here we have some specifications for this equipment at 1 GHz. So we can see that the S21 parameter uncertainty is as low as 0.05 dB, and the instrument matching is 1.02 to 1. So they are very good. Keysight has published some interesting data. We will present here 2 examples. The first example is measurement uncertainty of an LNA in an automated test environment based on a Monte Carlo calculation. They have tested a 3 dB LNA with a 15 dB gain and an input and output matching of 10 dB. We can see how the accuracy for the PNA-X technique is much better than the one using the Y factor, both in the case of using the DUT input or using the switch matrix. And we go down from an uncertainty of 0.75 to an uncertainty of 0.2 dB using the PNA-X. This is using the cold source method. This is another example from Keysight. So we can clearly see how the ripple is much better using the PNA-X method than using the traditional Y factor technique. Now we will present the calibration and the instrument setup. For the calibration, the required equipment is the calibration kit, the power meter, and the power sensors. Those are on the left graph. On the right side, we have the required equipment for the test itself. That's the PNA-X, for example, in our case, and of course, our device under test. We have listed the models we have used, but of course, you can use different models for the PNA-X, the power meter, the power sensor, and the calibration kit. The calibration process is very simple. First, you have to start by calibrating the power level. This is just connecting the power sensor to the power meter. Then you have to calibrate the PNA-X. So you have to set a lot of parameters, and we have listed here the main ones. The first one is the type of measurement. You have to select a noise figure cold source. Then we have chosen the vector noise calibration using the power meter. In our case, the PNA-X has an internal electronic calibration module, so we don't need an external one. The noise receiver has been set to 4 MHz and the IF bandwidth to 1 kHz. The noise averaging factor has been set to 50 to reduce the calibration and measurement jitter. Regarding the receiver gain, we have set it to lowest state, since in our case, gain plus noise figure is above 35 dB. Otherwise, the receiver would be incompressive. It means that, for example, if we are testing it in high state, our noise figure will be smaller, but it won't be true. Okay, so we have to be very careful of avoiding compressions and things from the equipment. Finally, we have set the input power level to -40 to ensure there is no compression from the DUT. If it is required, a source attenuator must be set for the whole process of calibration and test. It is very important not to change it between the first step of calibration and the test step. In our case, we have used a 10 dB source attenuator. Then we just follow the PNA-X with our guide steps. So we will have to start by connecting the power sensor to the input port. A higher power level is preferred to avoid S21 uncertainty, so it is 0 dBm. Then we use the calibration kit at the input and the output port to test the open, the short, and the low terminations. And we complete the calibration by using a coaxial through. This process will require more time than a regular S-parameter calibration or a noise figure calibration using a noise source, but accuracy is the most important parameter in our case, so it is worth it to spend more time. Here we have an estimation of the noise figure uncertainty calculated with the software from Keysight, which is running directly on the PNA-X. So it takes all the parameters from the setup and also from the DUT performances to calculate the uncertainty we are having in our case. It is running in real time. Okay, so we can see the changes and the effect of different parameters. We have the overall uncertainty on the bottom, and on the right side, we have the different contributions to our uncertainty. This is a general example. We will see later a specific example. So two standard deviations of the mean value covers the 95.4% of the possible results. In our case, our production flowcharts allow us to use only one standard deviation. If our device is not within the 68.2%, it will be measured again to check that our case is the corners of the Gaussian distribution and not it is not the mean value. If we have to test it again, we will do it. If we have to calibrate again, we will also do it. If the result is confirmed that the mean value is close to our result, and it is not a problem of the distribution, we will tune this device. And finally, if there is nothing we can do, we will reject it. Now we will see the measurements of two LNAs from our catalog. So this will prove the accuracy of this methodology. We are testing two Ka-band LNAs amplifiers using this method and the setup described in the previous slide. The first one is an LNA working from 17.7 to 22 GHz with a 40 dB gain and a noise figure of below 1.5, sorry. The second one works from 20 GHz to 22.5 GHz with a 45 dB gain and a maximum noise figure of 1.3. As I said, the first one has great performances in Ka-band with a 4.3 GHz bandwidth, a 40 dB gain, and a noise figure below 1.4 dB at 25 degrees all over its frequency range. The input port is a WR42 waveguide with an input matching below 2 to 1. And the output port is a female coaxial connector with an output matching below 1.8 to 1. It is extremely important to perform all the embeddings from extra losses you may have. So, for example, in our case, we have an adapter to change from the coaxial to the WR42 waveguide. And it is inserted between the calibration plane and our DUT. So we have to remove those losses from our result. Otherwise, the noise figure will be higher than reality. Here we present the measurements of the noise figure of one of these units and also the parameters. We see that the noise figure is below 1.3 dB at 25 degrees in the whole one with 17.7 to 22 GHz with typical values on the 1.2 dB. The S parameters prove that the S21 is around 40 dB and output matching is very good and input matching is quite good considering that this is an LNA. But these results doesn't mean anything if we don't have an uncertainty close to them. So here we have the overall uncertainty for 1 sigma, and the value is below 0.08 dB. And then we have the different contributions to check that all the parameters have been properly set in our setup. This guarantees that the noise figure is well below our limit specification of 1.4 dB, including the measurement uncertainty. As you can see on the right graph, we have the noise figure, including the uncertainty of plus minus sigma. Similar measurements in similar bands using the Y factor or other methods can lead to uncertainties as high as plus 0.5 dB and minus 0.4 dB, as we have seen in slide 12. This means that the measured noise figure value might be in range between 0.7 and 1.8 dB, which is a huge range. In this table, we have a summary of the specification values for this part number, and also the tested values we have in one unit. So, for example, the frequency is between 17.7 and 22 GHz. The small signal gain in this case is between 38.7 and 39.4, with a gain flatness of plus minus 0.3. The noise figure is below 1.3 in all the cases. The input matching is always below 1.9 to 1, and the output matching is 1.5 to 1 as maximum value. So all the parameters are achieved. In the second example, we are testing an LNA from 20 GHz to 22.5 GHz. So it is not covering all the Satcom frequency range, but we are getting a better noise figure with a slightly higher input matching, which is always below 2.5 to 1. So it is still a good value. And the external mechanical interfaces are the same. So we have a WR42 waveguide at the input and a female coaxial connector at the output. As in the previous case, we will have to perform an embedding to remove the extra losses from the adapter at the input. Here we can see the noise figure result, which is always below 1.2 dB at 25 degrees also in the whole band with 20 to 22.5 GHz with typical values on the 1 to 1.1 dB. On the right graph, we can see these parameters. So we can see that the gain is slightly higher than in the first case, with a very good output matching and a quite good input matching, also considering we are talking about an LNA. It's a very good noise figure. As done with the first case, we have calculated the uncertainty with 1 sigma. The overall value is below 0.09 dB. Of course, this is a negligible difference, but there is a difference of 0.01 dB between LNA1 and LNA2. This proves that the calculation is taking into account all the different parameters in the setup and in the DUT performances. So in this case, for example, we have a higher gain and also a different input matching, and we can see the effect of this in the final result. On the right graph, we can see the noise figure, including the plus minus sigma uncertainty. In this table, we can also compare the specification values for this part number and the tested results for this unit. So as we said, the frequency is between 20 and 22.5 GHz. The small signal gain is between 42.4 and 44.4 dB. So we have a gain flatness of plus minus 1 dB with a noise figure with a maximum value of 1.15 dB. A very good output matching of 1.2 to 1 and a quite good input matching of 2.3 to 1. Of course, as maximum value in the whole frequency range. So now David will finish with the conclusions of the technical webinar.
Thank you, Noelia. So let's summarize in 2 slides the conclusions of this work. So this first conclusions slide is about the technical points that Noelia has been describing. So the first one is that obtaining good values in the test is not enough if the accuracy is not consistent. So values or numbers like the noise figure, it might mislead us to false results. We need to select proper equipment depending on our requirements and the expected performance of our device under test. And of course, the calibration process is a key step. The plane has to be clearly identified and an embedded might be required if you place additional adapters or other items between the calibration plane and the device under test. The setup will affect the accuracy, of course, so it's recommended to sacrifice a few more minutes, a little bit of effort during the calibration step in order to avoid issues afterwards. You can have a big difference at the end in the accuracy if you don't do that properly. So when using the PNA-X, we have the possibility to check the uncertainty with the own instrument calculator. And this confirms our setups and the results are valid. This is a very useful information that we have to take in very good account. More general conclusions is that we have understood the difference and improvements of the cold source method with respect to the Y-factor technique and also other less used techniques. We have successfully implemented the cold source method in our test methodologies, and we are nowadays using it on a daily basis. We have been able to confirm the performance of our LNAs with great accuracy, and we have confirmed the state-of-the-art performance in Ka-band. And we will continue the monitorization of improvements on this field to maintain the edge, both with the measurement accuracy and with the performance of our low noise amplifiers. And this finishes our presentation today, and we will be pleased now to go over the questions and answer section. Thank you very much.
All right, great. David and Noelia, thank you so much for that great presentation. As David just mentioned, we are going to move into taking some questions from the audience. So guys, our first question today, can I use a scalar calibration instead of a vector calibration?
Sure. The scalar calibration is one of the traces from the vector calibration. Of course, the vector calibration is more accurate because you are performing a source pool. So you are changing the input impedance, and the scalar calibration only provides this result, so for a perfect 50 ohm impedance. So if your DUT has not very good S11, it is always better to check it with the vector calibration.
Great, thank you so much for that answer. Another question here, what constitutes a good load? Example, how good should be the match and how to connect it in an automated setup?
What is it? Could you please repeat? We are looking for the...
Sure, I can repeat the question. So this person is asking what constitutes a good load? An example, how good should be the match and how to connect in an automated setup?
So that's why it is preferable to use the vector calibration because you will change the load, and it provides you a lot of information, not only the 50 ohm result. What's good and what's bad, it depends on your DUT. If this, let's say, bad input matching at the input changes your results in your DUT, it means it is sensitive. And that's why it is much better to use the vector calibration than the scalar calibration. If your DUT is very well matched, it will be enough with the scalar calibration.
Great, thank you so much for that answer. So just a couple things before we move to the next question. There are some widgets along the bottom of your attendee console. And if you look, you can see that there is a copy of the PowerPoint in a PDF format listed right in your resource widget. If you'd like to grab that and take that with you today, that has some great information from today's presentation. All right, guys, so our next question today. NF accuracy depends on very good knowledge of gain to determine the slope. Full S parameters are typically best. Is there a tool to help assess scalar-only gain performance?
Sorry, could you please repeat again?
Of course, yeah, not a problem. So this person is asking, NF accuracy depends on very good knowledge of gain to determine the slope. Full S parameters are typically best. Is there a tool to help assess the scalar-only gain performance?
Yes. So, in fact, we are performing a calibration and a test in different channels. In the first channel, we are testing the full S parameters, and in the second channel, we are testing the noise figure and the S21. It is completely identical. So the S parameters are perfectly matched between only a S parameter calibration and a noise figure calibration. Of course, using this method, not using other methods. That's why it is so accurate, because you are perfectly getting the S parameter result.
Okay, great. Thank you so much for that answer. Another attendee here is asking, can this technique be used with devices with mixers and frequency converters?
Sure. The only important thing, of course, is that your equipment can test them. But this technique is perfectly adequate for these components.
All right, thank you so much for that answer. Another attendee is asking, how do I correctly de-embed the adapters?
So you have to calibrate the S parameters and to test the adapters. In our case, for example, we have a waveguide to coaxial adapter. So we place two, one against another one. So we have coaxial, waveguide, coaxial. And then we calculate the losses from only one adapter, and we apply that, the embedding, to our results.
Okay, great. Thank you so much for that answer. All right, another attendee is asking, changing to waveguide adapter requires knowledge of this loss. How do you de-embed this? And this may be connected to the question that you just answered, but I will ask it. This is in reference to table and back-to-back measurement.
It is exactly what we have just answered in the previous question, yeah. You just have to test the adapters separately, and then you apply the loss in your calculation.
Okay, great. Thank you so much for clarifying. This attendee is asking, is this technique applicable to assess the NF performance at high temperature? And in parentheses, it says, in a climatic chamber, on parentheses, in the calibration procedure application over a large range of temperatures.
Yes, of course, we use it. In fact, we have a climatic chamber, and we change the different temperature values, and we test using this technique. The only thing to take into account is that you have long cables from your equipment to the climatic chamber. So matching will be less accurate, let's say. And it also affects the noise figure accuracy and the S parameters. But it is, of course, possible, yes.
All right, great. Thank you so much for that answer. As I mentioned before, if you have a question today, go ahead and place it into the Q&A window and click Submit. We will do our best to get through as many questions as we can. If we don't get to your question, we will reach out to you following today's webinar. So if anybody has a question, now would be the time. Our next attendee is asking, what should I do if my PNA-X does not have the same internal EKI module?
So it is not a problem at all because there are ECAL modules that you can use externally to your equipment. And in fact, these tuners can be used also as calibration kits. So they are very useful devices.
Okay, great. Thank you so much for that answer. Our next question here, when do I have to perform a de-embedding?
Well, we have discussed it previously a little bit, but I will explain it in detail now. Every time you have a different element between your calibration plane and your DUT, you have to de-embed those losses, both at the input and the output. Talking about the noise figure, of course, the input is more important, but for example, for the S21 result, you will have to de-embed the losses at the input and the output.
All right, thank you so much for that answer. Another attendee here is asking, do you have any connections via Mondragon?
I take this one, Noelia. No, okay. Absolutely not. We are a private company funded by private individuals, not connections with the Grupo Mondragon.
Okay, David, thank you so much for that answer. As I mentioned before, if you guys want to grab that PowerPoint on your way out, feel free to click in the resource widget and download that. It's a PDF format of the presentation from today. All right, guys, our next question here. What happens if I do not use a high noise averaging factor?
So your accuracy will be lower. If you are only testing one time, of course, you have a big accuracy. If you are testing your device 50 times, you can get a much accurate result, and you will have more information, and you will be closer to the mean value of the Gaussian distribution. So, of course, it takes more time, but it is worth using a high value. It is not necessary to use a very high value. You just have to use, I don't know, 20 measurements or 50 measurements, not more than that. Otherwise, you will spend a lot of time in front of your equipment waiting for the result.
All right, great. Thank you so much. Our next question here. When should I use the Y factor method?
So first of all, when you don't have the equipment to use the cold source method, also when your noise figure is not very low, so for example, if you are testing a 10 dB amplifier, you don't, noise figure amplifier, of course, not the gain, it is not required to use the cold source method. And also, for example, if your matching is very good, or it does not affect to have a mismatching at the input, you may use the Y factor method.
All right, thank you so much for that answer. So just for our attendees, if you do have any questions, now would be the time to answer or to enter them into the Q&A window. We are going to wrap the webinar up shortly, so we do have some questions we have not answered yet, but we will reach out to you all following today's webinar. So I'll give you all another minute or so to ask any questions that you might have. All right, guys, it looks like we have another one here that just came in. This person is asking, it's another question about the de-embedding of the adapter losses are performed through subtracting at the instrument or numerically after getting the data.
So both options are possible, but we prefer to do it after getting the result because you can use a very good calibration to characterize your adapters. But it is also possible to normalize your result during your test with the equipment in real time. So both of them are possible.
Okay, great, Noelia. Thank you so much for that answer. We have time for about one or two more questions, so we're going to take this attendee's question next. Do you measure two identical adapters, take the total S21 and divide it by 2 to find the insertion loss of just one adapter? What about S11?
So yes, we take two identical adapters and divide it by 2 because it is what we can do with the calibration planes we have. And it is not a problem. I mean, the S11 will be affected if the adapters are not very good. In our cases, we are using adapters, so they are very well matched and they don't affect the result from the DUT.
Okay, great. Thank you so much for that answer. All right, we're going to take one more question today, and then we are going to start to wrap things up. Okay, this person is asking, if the accuracy is so important, why did you choose 1 kilohertz as your IFBW? Is that better to have lower IFBW?
Yes, in general, it is better to have a lower IF bandwidth. In our case, it was okay with 1 kilohertz, and we also need a trade-off between time and accuracy. So if you choose a very low IF bandwidth, you will spend a lot of time waiting for the results, especially when you have an averaging of 50 results. And it was clearly enough in our case. Of course, in a different case, you have sensitivity to this value. You will probably need to lower the value.
All right, thank you so much for that answer. So as I mentioned, we are going to start to wrap things up. If anybody does have a last-minute question, you can still enter it into the Q&A window and click Submit, and our team here will get back to you following the webinar. So feel free to enter a question now if you have it, and we'll get back to you following today. So a huge thank you to our presenters today, Noelia and David. Thank you both so much for a great presentation and for taking time to answer so many of the attendees' questions. We enjoyed having you. Thank you both.
Thank you, Katie.
Thank you very much, Katie.
All right, and thank you guys. Again, thank you all for taking time to attend this webinar event. Take care, and we will speak with you all soon.